In this problem, we're going to look at the effect of diffusion and momentum um, on a water parcel. We have here a water column. Z is the vertical coordinate, so this would be the free surface up here at 0. And we have some measurements of the velocity in the water column. Here, the u velocity, actually this should be centimeters per second, the u velocity as a function of depth. So at 5 meters, we have roughly 50 centimeters per second, and we see it decreases as we go down. Going down, let's follow the black profile. As we go down the water column, the velocity is decreasing. So this could be from something like a wind stress at the surface, generating this particular vertical profile. We have in this case a vertical shear, meaning that the u velocity, which is the velocity in this direction, is changing in this direction in the vertical. So there's a rate of change. We think of this as a shear. One way to think of it as a shear is if we look at this water flow at an instant of time. If I were to tag a set of particles, something like this, in the water column at some time t, and then I see what happens to this rectangular tag set of particles. Well, the top edge of this rectangle is moving at a higher velocity than the lower edge. So some later time we end up with a rectangle that looks like this, that's sheared over. Turns into a parallelogram like this. And so that the action of that is shear. The question we want to answer is, for this particular setup, and I'm referring to the black line here, looking at this mid-depth right here at 35 meters, the water right here, is this water subject to an acceleration given the vertical shear in the water column here? So does having a neighboring parcel up here moving faster than our parcel of interest here, and a neighboring parcel deeper moving slower than the parcel of interest, do those have some influence on the velocity of this parcel at a later time? And we can look at the momentum equations to try to see what's going on. So let me back up to get some blank space up here. If we think about this, from the point of view of the momentum equation, let's get rid of this hideous purple color. And we have du dt, so the rate of change of the u velocity, so this is an acceleration term, is going to be equal to the forces that we've been through in class. So you have the pressure gradient minus 1 over rho dp dx. We have a Coriolis plus Fv. We have 3 diffusion terms. I think I may run out of space, so I'm going to put them on the next line. Plus partial x of AH times partial U partial X plus a very similar looking term in Y, partial Y, of AH times du dy, plus the third diffusion term, partial Z, this is the vertical coordinate, times what is sometimes written Km, and I'm going to write here as AZ, that's the other symbol that's sometimes used, partial U, partial Z. These are what are known as the diffusion terms. There's 3 of them in each of the momentum equations. They look fairly similar. You can see here, if you take these constants out, or not constants, these variables out, these are the diffusivities. And here we have chosen to separate them into 2. There's an AH, which relates to the horizontal component, horizontal diffusivity, and there's an AZ, which is the vertical value. And so in the ocean, it's anisotropic, so we consider these values separately, the horizontal being different from the vertical. If we remove those from these derivatives, we can see, for example, if AZ were constant, which it is in this particular case, this problem we're working on, if we pull AZ out, we end up with this last term in this equation looks like this, partial squared U, partial Z squared. This is a second derivative of the velocity with respect to Z. So if the diffusivities are constant, what it requires is that for these diffusion terms to be active, we need the second derivative of the velocity to be non-zero. So the velocity can't be constant and the velocity cannot be linearly varying. There must be a second derivative variation. And we'll see a bit more intuitively why that is when we go to make this calculation. So in thinking in terms of this equation, what I'm focused on in this problem, we're not talking about pressure gradients or Coriolis at this point. We're asking about diffusion, and particularly the diffusion that's resulting from shear in the water column. We're only given u as a function of z. That's the only information we have. So we're going to assume that these terms are 0. We're going to focus in on this particular, actually I'll keep it in this case, in this particular term right here. We're going to focus on asking ourselves, what is the value of this term? You're given in the problem the value of the diffusivity AZ or Z, which is units of meters squared per second, is equal to 0.01 meters squared per second, which is a good representative value. So we're going to go back and make a computation of this. Now we don't have u directly as an analytical function of z, from which we could take a second derivative. All we have is data, and this data is supplied to us in this profile at these regularly spaced points, which are all 10 meters apart. So we're given data every 10 meters. We're given it at 5, at 15, at 25, at 35, 45, etc. So we're given data every 10 meters. And so what we have to do is go back and approximate this second derivative. So if I look back here, and I'm going to ask myself, how can I get an estimate of this term? So the term again looks like this: partial z of az times du dz. So what this is the rate of change with respect to z of this thing right here, az du dz. So the rate of change with respect to z of az du dz, this du dz is a derivative of u with respect to z. So I'm looking at the rate of change of the rate of change. And so we need an estimate of this at two different locations, and then we're going to take a derivative of that. Az we can pull out, so I'll leave this as equals az. Because it is constant, I can pull it out. ddz of, and I'm going to put in parentheses here, du dz. Looking back at our parcels here, how am I going to estimate this? Well, I have a second derivative, and to estimate a second derivative, I need at least 3 points. 2 points of information can only tell me a rate of change, a slope. Can only get to the first derivative. I need at least 3 points to do that. And what I'm going to do is, this is my point of interest, is I'm going to estimate that partial u partial z at this location, which I'll mark with a blue dot, and I'm going to estimate it at this location here. So between the upper parcel and the parcel of interest, and between the lower parcel and the parcel of interest. At these two interfaces, I'm going to estimate partial u partial z. That's what I would like to get. And so an estimate of partial u partial z is we can get from just a divided difference, delta u over delta z. So delta u over delta z at this interface right here requires me to take this u here minus this u right here and divide it by the distance between them, or 10 meters. An estimate of this derivative right here, or sorry, this derivative using divided differences at this lower interface is going to be equal to this value here minus this value here divided by the distance between them. So I can go ahead and write that. What I've named these, I've given these identities. This one is k plus 1, the index for this particular velocity. My velocity of interest is velocity k, and the velocity below it is k minus 1. Those are the 3 data points I'm going to use to get at this estimate. So if I come up here to where I'm doing my estimation, I can see I can write this as az times the derivative of az times this upper value. So I'm looking at du dz, how this changes with respect to z. So this, at the upper interface, this du dz is going to be u at k plus 1 minus u at k divided by the distance between them. This is simply an estimate of du dz at the upper portion. And what I'm going to do is take the difference between this interface, the value of the gradient at that interface, and the interface below, uk minus uk minus 1, over delta z. So those are two different estimates of du dz. One is above, one is below. And now I'm going to estimate the derivative the rate of change of that gradient. So this gradient here and this gradient right here, divided by delta z. In fact, I think I've written them backwards here, so let me just repair this so that the value comes out correctly. So we have, let me just go back down here. I'll point out which is which here. So this one right here, this upper interface is going to be, the estimate of the gradient, this upper interface is going to be uk plus 1 minus uk over delta z. And at the lower interface is going to be uk, my point velocity of interest, minus uk minus 1 over again delta z. So I will have here the difference between them, which I can write as uk plus 1 minus uk over delta z minus uk plus 1 minus, uk minus uk minus 1. That's the lower gradient. But I want the gradient of the gradient. So it's the difference between these two gradients divided by the distance between them, delta z, all times az. And what I see here is I can simplify this formula, and I have az. I have a uk here, minus, and I also have a minus uk here, and this minus times this minus becomes a plus. So if I write this out, I'll get uk plus 1 minus 2 uk plus uk minus 1. And this is divided by delta z, and divided by delta z, divided by delta z squared. This is, in the brackets there, this is what's called a central difference approximation of a second derivative. This is an approximation of partial squared u partial z squared. This is the classic approximation of that using what's called a three-point stencil, 3 pieces of information centered on k, centered on our point of interest. Multiply this by az, and we have this, an estimate of our term using 3 points of information. An estimate of that second derivative is what we have. If we plug those values in, so for example, uk plus 1 is 44 centimeters per second. uk for the black line, so again, let me go back here and clean this up. What I'm thinking about for the first computation is this, I'm assuming the water profile follows this black line like this. So I'm going to use this value here, which is 26 centimeters per second for uk, and I'm going to use k minus 1 is going to be 20 centimeters per second. So if we put actual values in here, which I'll do in one example here, I have az is 0.01, that's meters squared per second, times uk plus 1, which is 0.44 meters per second, minus 2 times uk, which in the first example is 0.26 meters per second, minus 0.20 meters per second, that was uk minus 1, divided by delta z, which is 10 meters. So the distance, when I'm computing these gradients, the difference between this and this, if I'm computing a du dz, I take the difference between the values there divided by the distance between, which is 10 meters. It's 10 meters between every observation. That gives me an estimate. I might assume it applies to this interface between these two layers. And then I do it between my point of interest and the lower point, and it gives me an estimate here. And the distance between those two interfaces is also 10 meters. That's why we have the delta z squared. And so I can write this divided by 100, which is 10 meters times 10 meters. Close this up. These are just numbers at this point, and my result is going to be is going to be 1.2 e to the minus 5. That's meters per second squared. It's an acceleration per second squared. Okay, so about the same order as we found when we looked at the Coriolis force is the kind of numbers we'll see looking at pressure gradients later. Works out in this problem. It is a positive acceleration. And so we have to think about, well, does it make sense that it's a positive acceleration? If you go back to this diagram and think about what's going on, we have this parcel right here. It's being influenced directly by this velocity here and this velocity here. And so that influence comes through the shear in the water column. And the strength of the influence is dependent on the diffusivity value, which is constant and is in the same in the entire water column, so it's not varying in space. And so the upper parcel we see is traveling faster than this lower parcel. In fact, it's going 44 centimeters per second compared to 26 centimeters per second, so it's going 18 centimeters per second faster. And then this lower parcel is going slower, but it's only going 6 centimeters per second slower. So the upper parcel is going considerably faster. And so that'll have a greater influence. And in a sense, when we compute these gradients, the gradient, du dz, is greater on top than it is on the bottom. So the contribution to momentum is greater. The contribution to momentum to the top parcel is adding to the momentum of this, while the lower parcel is trying to subtract from the momentum, is trying to slow down our parcel of interest in the middle here. But the upper parcel is having a greater effect because it has a greater velocity, and thus we have a higher rate of change of velocity, higher shear across here. So that upper parcel essentially wins out, and we have this central parcel, or parcel of interest, is going to be accelerated in this particular setup. So if this was time t equals 0, at some later time it's going to be moving faster. And in fact, if these parcels right here, don't change velocity for whatever reason, if they're stapled in time, and their diffusivity is constant, the result will eventually be that the parcel here will be exactly in between these two speeds, that they're both having the same influence. And if we think about the gradients are the same, and our diffusion is a rate of change of the gradient. And the rate of change of the gradient will be 0. And we can also see that our vertical profile here is linear. There's no second derivative in that profile. It's a line. The second derivative of a line is 0. We have that, and this again is assuming constant diffusivity. So that would be the case if somehow magically the top and bottom parcel would be uninfluenced by anything and just are motoring along at constant velocity. That central parcel will eventually accelerate until it's in this setup. It's exactly tugged between these two parcels. Which brings us to our other setup, this red line here. The only difference being that we've allowed our central parcel to start out at a higher velocity. If we go through the same computation up here, the only number that's changing in our formula up here is our central number. This number right here is now 38 centimeters per second. And so now we see the difference between the upper parcel and the middle parcel, 6 centimeters per second. And the difference between the middle parcel and the lower parcel is 18 centimeters per second. So we swap the differences. Now there's a much larger difference here than up here. So intuitively we can see that it's going to slow this thing down. And the math tells us, because we swap the differences, that the result is just going to be simply minus. It's going to be a minus 1.2 e to the minus 5 times 10 to the minus 5 meters per second squared. And that's because I picked the numbers, so they ended up just swapping over, not necessarily, it won't always come out like that. So just two different setups. In one case, the parcel is going to be accelerated in our black condition here. In the red condition, it's going to be decelerated because it has stronger influence from this parcel below here. So this has large implications on a few things. I'm thinking about boundary layers, thinking about wind mixing in general, because the wind, when it blows on the surface, here's the surface of the ocean. The wind affects only the surface, it applies a stress. In fact, the surface, it drags it along. And so if a water parcel is down here, how is it ever to know about the wind? How is it ever to be influenced by the wind? And the reality is, as the wind starts tugging the surface along, it can start influencing. Basically, momentum diffuses down into the water column through these mechanisms that we've been talking about. So if initially the water velocity is 0 everywhere, and then the wind comes along and says, oh, oops, didn't mean to do that. And the wind comes along and says, okay, I'm going to start the top layer moving like this. If this happened to be our parcel of interest here, we can see that there's a positive gradient up above it, and there's a 0 gradient below it. So the lower parcels are having no effect on this upper parcel. They aren't adding any momentum, they aren't subtracting any momentum, but the parcels above our parcel of interest are going to be adding momentum. So our parcel of interest is going to start to move. And sometime later, this profile might look like this. Oops, I don't know why it does that. Look like this. So it's constant velocity here. Now the gradient's right here. And same thing. So we have a parcel of interest down here, which is going to be subject to the exact same things that we saw up above. And so eventually the wind mixing, effectively what we've done is take momentum from the surface and diffused it slowly down into the water column until it results in a profile that might look something like our black case here, where we have the strongest velocities at the surface and weaker velocities down below. But the reality is that the wind can have an influence on the water column at greater than zero depth because of this transfer of momentum that occurs via this term right here. So the wind's going to transfer its energy from the surface is going to get transferred down. The momentum that in parts of the surface will be transferred down via this term right here. And then other terms will come into play, Coriolis, this and that. But this is a mechanism by which the wind gets down into the surface.